All right, everyone, 4142, we'll start with those, and then we'll jump into the first two sections of chapter 5 this week. So 41 and 42, as I mentioned, very similar. 42 is just going to be the applications of this. And as I mentioned, for all of you that plan on taking calculus, which is probably the only reason you're in pre-calculus, and here's one of the most important concepts that you will be talking about over and over and over in building from the start till the end in calculus. All right. And believe it or not, it is with our very basic linear functions that we started learning when we started talking about algebra and adding two variables into an equation. All right. So I'm going to run through this with you. Stuff you should already know, then I'll expand on the things that are newish. Okay. So a linear function, hopefully we all know that is our y equals mx plus b is our preferred or favorite form, but that's when we have y equals with an x to the first power. Okay, that's what makes it a linear. Now remember, to be a function, they'll tell us this, but that means to us, which we learned in chapter 3, that it passes the what?
Vertical line test.
Very good. And notice it passes all of those. Which you also may notice that there's one other scenario with a line that is not there. And that is whether we have positive slope, negative slope, zero slope, it's just flat, we call a horizontal line, but there also could be a vertical line. Why is that not listed, even though it is a possibility? We're talking about functions. And this does definitely not pass the vertical line test. Okay, so it's not that we can't have that, it's just not a function, and that's what we're talking about, are only things that function well. All right, so this is called slope intercept form because it gives us those two things. The only thing that is not listed is what intercept that represents, and you need to know it is the y-intercept. Okay, so that is where it crosses through the y-axis, and remember that B is what we're going to do in the order of the alphabet. We're going to label that first, where it crosses through our y-axis, and then from there we will build our line by, remember, we need a minimum of 2 points, our slope, which is, remember, our rise over run. Remember, we also talked about increasing or decreasing. So we said that we would read that from left to right for our x values, smallest to biggest, and see what our y values do, whether that's up and increase or down and decrease. Now, this is obviously called the constant function because what are our y values going to be constantly as our x's get larger? The same value. Okay, so how do we tell whether it's increasing or decreasing? Very simple with lines, because it's always going to be increasing or decreasing, or not either increasing or decreasing at a constant rate of change. Yes, I did say rate of change again. Hopefully you caught that. All right, we'll get to that in a minute. So if we ever have this form, our y equals mx plus b, slope intercept form, all you need to tell is if it's increasing or decreasing, you need to know the slope. And remember, if that is not there, then it's just y equals some number. They're telling you what y is always, no matter what the x value is. All right. So in order to find the slope, remember, it's very simple. We will just take the difference, we call it. They use the Greek letter delta. You guys may be familiar with that because of COVID right now. Okay, it's the new variant that came out. They're using the Greek letter. That is the change. That's the symbol we use for change or difference, okay? This is also a symbol that we use to find the change or difference, right? So if we have 2 points, we will take the x1, y1 and the x2, y2 and find their differences. Now remember, that was also the rise to our wives, run from our exes. Barrett knows what I'm talking about, I can tell. All right, thought it was just me. All right, so rise over run, that's how we find the change from one point to another. And if it's positive, we know it's an increasing function. If it's negative, we know it's a decreasing function. And if it doesn't change from one to the next, we know it is a constant function. Right? Now, there are other forms of lines. You guys may be familiar with this one. Or sometimes they have the A, B, and C all on one side. Okay? This is what is called standard form of a line. Now, how should you be able to tell it's a line still? The X and the Y are to the first power still. Okay? But this is another very important form that you guys will use over and over and over in calculus. I'm going to put stars by it. Our slope intercept, we already went over. That's our y equals mx plus b. And we can put f of x if it's a function. It passes that vertical line test, makes it more powerful. But does anybody remember the point slope form? Not many do, because it's not as widely used. It doesn't really help us to graph. This is by far our favorite. Okay, this is our preferred form because it gives us the slope and the y-intercept, and we can plot our y-intercept, do our slope, rise over run, whatever it looks like, graph, and we're done. But the point slope form I'm going to show you actually comes from this formula, our slope formula. Remember, it was y2 minus y1 over x2 minus x1. But notice this has 2 points. With this form, it only has 1 point in the slope. Obviously, there's our slope. So what I'm going to do is I'm going to actually get rid of our second point. So now I have my x and my y just like all these other forms, whether it's standard or slope intercept. But obviously, I like these because they're equations without fractions. I don't like this equation because it has a fraction in it. But the cool thing is, I know what this means. It means to divide. And we know how to undo that, the inverse of dividing, and that's multiplying. Now, again, to keep my equation equal, I'm going to have to do it to both sides, though. So I'm going to multiply both sides by that x minus x1. Remember, I just got rid of the 2 because we don't want 2 points. We just want 1 point in the slope. And by doing that, I now have my x minus x1 cancel with the other one. I know anything divided by itself is 1. So what's left is a y minus y1 on one side equals on the other an m times the x minus x1. And hopefully you guys do recognize that form now, because this is a very important tool that you will use over and over and over and over in calculus. Okay, and the most important thing that you guys will have to find is the slope at some point, x1, y1. All right, so make sure you write this one down, make sure you memorize it, and hopefully you now see where it came from is just one simple step. It was our slope formula rewritten without having the 2 points and getting rid of the fraction. All right. Now we mentioned the horizontal and vertical lines, those special scenarios where a horizontal line is going to tell you where the y's are something everywhere. Okay, that line. So they're just going to give you what y is equal to, some number. Where if it's a vertical line, notice they didn't put f of x. We can't put f of x because remember that was our y value. So now they're just going to tell you what x is equal to, some other number. So again, if I was to graph a x, pick your favorite number, say it was 3, you'd go right 3, or if it was -3, we go left 3. And then I'd tell you, well, it goes straight up and down because as long as x is right 3, y could be whatever. Right? So that's the difference between a vertical and a horizontal line, and of course, their graphs. Okay, just a quick review of lines. Now, what if we have more than one line? Well, then we want to look at their relationship. And one of the most important relationships that we will talk about is the fact that they are parallel or the special intersection of perpendicular. Right? And hopefully you remember, if we have more than one line, we want to know, first of all, what those mean. And hopefully you do. Parallel means that they will never intersect. And the only way that two lines will never intersect is if they have the exact same slope. Right? So that's what they're saying here, is that the slopes are the same. But even if those are the same, you do have to make sure that these are not the same. Because what if both the slope and the y-intercept were the exact same? What are we talking about here?
A meeting.
Yeah, the exact same line. And therefore they would not only meet, they would overlap. It would be the exact same line. That is the exact opposite of parallel. Parallel means they never touch. These intersect and touch every single point on them. Okay, so there is one little caveat, one catch, that they are parallel only if their slopes are the same, but these cannot be the same. Otherwise, it's the same line. Okay, and hopefully you remember what it means to be perpendicular. You should, because the x and y axis are perpendicular. They form a 90-degree angle, and not just one, actually 4, but we'll just focus on one. That's what it means to be perpendicular. So if I was to draw a line this way, which is what kind of line?
Increasing?
Very good, Taylor. From left to right, that is increasing, which means it has what kind of slope?
Positive.
Good, Julian. What would I have to draw in order to make them perpendicular?
A decreasing slope.
Which means slope of what? Very good. Somebody put in the chat, negative. So I would have to draw something like this. Now we know what perpendicular means. It forms that 90-degree angle. But notice that this would be a positive or increasing, and this would be a negative. So we know for a fact that their slopes, one has to be positive and one has to be negative. We call those what one word? Do you remember from last week? Opposites. But there is one other thing. They're not only going to be opposites of one another, they're also going to be what is called reciprocals. And again, getting that terminology down will help you. So perpendicular, they have to meet two criteria. They're not only opposite slopes, they also have to be reciprocals. Okay, you got to check off those two things pertaining to their slopes. Right? So a lot of people say, well, if you just multiply them together, you'll always get a -1. Because if I have A over B as one of my slopes, what would the other one have to be?
Negative b over a.
Very good. And if I multiplied this times that, notice positive times negative is going to be negative, and then b over b, a over a would all cancel to be 1. So that's the quick, easy way to check, but I think it's easier to just do that. Is one positive, one negative? Definitely not parallel. It could be perpendicular if they're reciprocals of each other. All right? So just a quick little review and overview of lines. That's it, my friends. That's 4.1. And 4.2, this is all the applications of that. So unless I sit here and do a few variations of examples, there's not a whole lot of notes, but I did say applications, you know what, those are word problems, and those are scary for a lot of math students, right? But don't be afraid. Here is a 7-step program to try to help you through these, all right? But the key is when you have a word problem, just read it slowly, right? And I don't mean that's not what I mean by slowly. Okay, what I mean by slowly is write down what you know as you go. And my suggestion is read the whole thing first without writing anything down. I want to know what they want to know. Read the whole thing and it's going to tell you, find this. So you already know, well, that's an unknown. So I'm going to call that X or whatever letter you choose. And then go back and say, all right, well, what did they give me to find that? And then, as you will find out in math, you will take that information, one that they asked for, and then the other things that they gave you, and then you'll try to put it into an equation so that you can then solve using all the things that you've learned up to this point. Okay? So whether you use this 7-step program that the book suggests, it's all good. Just solve it and make sure, first of all, that you can show me what you're doing and how you got there. You know me, I don't like just answers. Okay? So that's it for chapter 4. That's all we are going to do today and the rest of the week for those of you that haven't started or finished the homework. All right? Otherwise, we're going to go ahead and move on to chapter 5. And this is why I told you to hold off on that question earlier, because as you can see, we're going to move from lines, linear, where it was just y equals x and some stuff, to the first power, and we're now going to increase it by 1. We still have our x to the first, possibly, but now it's going to be x squared. And remember, we call those quadratic functions. And this is what makes it a quadratic. Right? Now, hopefully you remember the graphs of these are parabolas. And those are some of the things that we worked on last week in chapter 3 already. Okay, because those are functions, you can see again that it would pass the vertical line test. But we also talked about inverses, and we said this would not. We would have to get rid of 1/2, and now it would have an inverse. Okay, so there is what is called a general or generic form, which we don't prefer. As one of you mentioned from last group quiz, how do we even do that? I'm going to explain it more today. This is what is called standard, or what I like to call it even better is vertex form. Do you guys recognize the HK stuff that we talked about? Remember, that is just our x squared, our parabola, and the h and the k are what we shift, right? So our vertex will then be that HK. And remember, it's the opposite for the x's, and the y stays the same, right? So that's why even though it was a negative h there, I took the opposite so that we could put positive h there. Right? That means it could be positive in there, like 2, then we would say the opposite and put -2 comma something. And by the way, guys, if we find our x, then don't they already tell us what the y is? So that's the key. If we can figure out what x is, then we can plug it in, do whatever it says in the order of operations, and figure out what our y value is. right? So I'm going to show you why this is in that form in just a little bit, okay? Otherwise, make sure that you write in your notes the two different forms, the generic form where it's just multiplied out, expanded, or the preferred standard or vertex form, which gives us the H and the K. Now, this is a little thing that I will mention a little bit later, but Taylor wanted to make it a point. Notice that they said that the H, if it's in this form, is equal to negative B over 2A. And the K, we could just plug in the H into our function, whether it's there or those two spots to find our Y value. All right, so I'll go over that a little bit more, and then we will expand and talk about some of the things that we talked about last chapter when we were dealing with all different sorts of functions, not just lines or these quadratic parabolas. Okay, you guys remember domain and range? Do we need to review that at all? Input outputs usually are X values and our Y values. Our max and mins are those high and low points. And remember, we talked both about local max and mins versus the absolute or global max and mins. Hopefully you remember the difference between those. And then something that we mentioned a little bit, but want to expand on. Do you guys remember X and Y intercepts? Where it crosses through or intercepts our X axis, and where it crosses through or intercepts our Y axis. And of course, if this basic Y equals X squared has some other stuff rather than just it, then it's going to be taken and shifted either right and up, left and down, up, whatever, or even expanded or condensed, shrunk. Okay, all those different things that we talked about, it can even be flipped the other direction by making that A in front of the X squared, which makes it a parabola, a negative. Okay, so before we get into that, remember, if we're talking about intercepts, there can be no x-intercept for these parabolas, but there will always be a what?
Y-intercept.
Y. WHY. Not emphasizing Julian's correct answer. Go ahead, Corey.
Because of the horizontal line test.
Okay.
And the arrow on the parabola goes to
Good.
infinity.
Remember, we're talking about parabolas only opening up
Oh, gotcha.
and out or down and out forever. So what is the domain of every single parabola?
Negative to positive infinity.
Very good. But is the range always going to include every Y value? Obviously not. We're missing all this down here. Okay. But we will have an X and X and X and X value for every direction because this goes up and out forever or down and out forever. Okay. Even if it's really narrow and they put a 2 in front of the X squared or a 3 and it goes up 3 times as fast, it still goes out forever. So the domain for these quadratic functions will always be positive to negative infinity. We're never going to include those, right? But the range will change, and that will be dependent on its vertex and its direction. So sometimes we will never have an x-intercept. Sometimes we will only have one when our vertex is on. Most of the time we will have what? That's right, Barrett. Whether it's facing upwards or it's facing downwards, we will have 2. Okay, very good. How do we find those exact places? Because they are important and they're going to allow us to graph these things. How do we find them? How do we find our X and Y intercepts?
Adding 0 to either the domain or range, and then solving the problem.
Very good. If you want to know where our graph intercepts or crosses the x-axis, what does that mean is true about this point, this point, this point, anywhere it crosses? What is the one thing that they all have in common?
Y is 0.
Very good. This is 2 comma something. This is 1 comma something. This is 3 comma something. But what is that something always? 0. When you are along the x-axis, that means you are not up or down any. So to find your x-intercepts, my friends, all you're going to do to find the x is let y be 0. And you can probably guess what's going to happen if we want to find the y-intercept. Where does it cross through the y-axis? Up here, here, or there. What's going to be true about those values? It's not going to be any right or left. It will be up or down some y value. So again, to find the y-intercept, we will let x be 0 and find that y value. Now, one is obviously easier than the other. Which one's a whole lot easier to find? The x or the y?
I want to say Y.
Y. W-H-Y, Corey. Remember what we said, whether it was generic in that general form or in that standard vertex form. What did they give us?
The Y.
Exactly. They're telling us what y is equal to. And we said if we knew what the x was, because those A, B's, and C's or H's and K's are going to be numbers, if we knew what the x was, then we could plug it in here or here and then work it out, and figure out what our y is equal to. So absolutely, it's much, much easier to solve for the y-intercept. And somebody put, it's easier because it's just 1 point, for sure. But this is even more so y, and that's because it's y equals already. They're telling us what y is equal to. We just plug in what for x? 0. Very good. And which one of those two would you prefer to find the y-intercept? The general form or the vertex form?
General.
Yeah, because what's going to happen to this and this?
Both is 0.
Because anything squared that is 0 or multiplied times a, and anything multiplied times whatever that b would be, would all go to 0. So what is our y-intercept always going to be? Whatever that constant is, that c. Very good. All right. But here, if I put in a 0 there, what am I going to have to do? Add or subtract that h, square it, multiply it by a, and then add k just to find my not preferable. But sometimes we'll have to do it. Okay, very good. So to find the x-intercept, we let the y be 0. To find the y-intercept, we let the x be 0. So if you ever want to find the intercepts, you just let the other letter equal 0 and find the one that you wanted. You get rid of it. You get that one equation with just one of the unknowns. Okay, but as we mentioned, the x is going to be a little bit more difficult, right? Because now we're going to set this whole thing equal to 0 or this whole thing equal to 0. And that's going to be a little bit more difficult to solve for x. So how do we do that when we have these quadratics? the number one thing that we want to do is try to factor. Okay, the second and third options are totally up to you on whether or not you know how to use the quadratic or complete the square. And it's going to depend on what you're given. But these are 3 techniques that you all should know. Does everybody remember how to factor? We reviewed that a little bit, right? Do you remember the quadratic formula? Anybody recite it?
Yeah, okay, so not 100% on this, but I'm pretty sure it's x equals negative b plus or minus the square root of b squared minus 4ac all over 2a.
Hey, you should be 100%. That's very good. That's what it is. Let me ask you an even further question. Do you know why it's that?
I don't. I just know the formula.
Yeah, most people have never seen why it's that. And that's what I want to do in this class. You guys already know how to factor. You already know the quadratic formula. You probably forgot how to complete the square. So by doing this one thing, it's going to hit all those points, and I'm going to prove to you right now why it's this. All right, you guys ready? Check this out. It's pretty cool. I'm going to take my y equals ax squared plus bx plus c. And we're going to make that y equal 0, as we mentioned, right? So now I'm just going to have that this whole thing is actually equal to 0 now instead of y. I'm trying to solve for x. The problem is I don't know what a, b, or c are. They're random numbers, right? Could be positive, negative, whole numbers, fractions, decimals, whatever. So what somebody figured out was, I don't want to try to factor this every time because there's things that don't work very well. You guys know, especially when you have a number in front, you're like, I don't remember how to do those. I only do the ones with the x squared. But you should still know how to factor that. The guess and check, over, under, AC method. People know all kinds of different ways, okay? But what I'm going to do is I'm going to solve with A, B, and C still in there. But as you said, I don't like the x squared to have a coefficient in front. So check this out. I'm going to divide it out. Now, can I just divide everything by A if I wanted to? Yes, only because it's a number. You cannot do that with a variable. Because what did we mention already before? What do we not know how to divide by?
0.
Very good, Julian. By 0. And I know that this can't be a 0 because if it's a 0, then we don't have an x squared and we have a line and we don't need to do any of this. Okay? But an x, we don't know what it is. It's a variable. It can vary. It can change. So I can go ahead and do this. You know what? Before I do that, I'm going to get rid of the c. I'm concentrating on solving for x, so I'm going to move this over. So now I got the ax squared plus bx equals a negative c. Now I'm going to go ahead and divide everything by a. So that that is gone. And now I have x squared plus b over ax equals negative c over a. Everybody good so far? Now, I still want to solve for x. The problem is there's an x here and an x there. And I can't just factor out an x because now I'll still have an x. So I'm going to have to use this thing called completing the square. And if you don't remember completing the square, that's why I'm doing this. I'm, as they say, feeding 2 birds with 1 stone. Instead of killing 2 birds with 1 stone, that's just harsh, right? I'm going to show you why this is what it is and go over completing the square. So I'm going to go ahead and add some number. And as long as I do it to both sides, then it will still remain balanced or equal. right? What number? Does anybody remember what goes in that blank, that square, in order to complete the square? It's all right, that's what I figured. That's why I'm going over it. Completing the square to figure out what you're going to add in order to force it to be nice and factorable and look like this, which is why they call it completing the square. So that this is factorable and not just any two factors. I get whatever in there that's in there so that I can rewrite this as that thing squared. I'm going to take half of this and I'm going to square it and put it in here. Because as you guys hopefully remember from factoring, I know the x times x is going to give me my x squared. But I need something times something to give me this. And if it's the same, then remember when I do my foiling or distributing, I'm going to end up having two of them here. Which is why I'm going to take half of it and then multiply it times itself to go in there. So I'm going to go ahead and write this out so that you can see it in a different color. What is half of b over a? It's b over 2a. And what happens when I square that? I get b squared over a 4 and an a squared. Now, normally I wouldn't do this, but just to show you, if you factored this, which remember, I'd have to do it on the same, on the other side. I would have my x times x to get my x squared. But what times what is going to give me that? Well, isn't it this? Isn't it my half of b over 2a? That'll definitely give me this when I multiply it, right? So if I put that b over 2a here and here, and since these are both positives, I'm going to put a plus sign in between them. We know that this times this gives me that. We know that this times this gives me that. But what about when I multiply this by an x and this by an x? What will I end up having? That b over 2a times x twice. And if I add that b over 2a to itself, I'll have it twice, which means I will have two b over 2a's times the x, which means I have what I started with. So hopefully you guys see that this is equivalent to that. But what does this allow me to rewrite it as? That, instead of writing it times itself, I'm going to write it squared. And what is it equal to on the other side? Well, this is a mess, isn't it? So I'm going to do what it says, and I'm going to add these two fractions. And in order to add fractions, we need a common denominator. And since this is 4a squared, and this has an a, what am I going to multiply this by? That fancy one. Of what, Barrett?
Yeah, 4a squared.
Careful. I don't need the squared. I just need a 4a, right? Because I already have 1a down there, and that would now give me my 4a squared. So I have, Zenon's already seeing it. He's like, this is awesome. Mind blown emoji. He's going to send it in a minute. All right. But check out, what do we have on top? We got a b squared minus a 4ac. Now, don't forget, we're trying to solve this for what? X. So now I had two x's. Now I got it down to just one. So I'm going to undo everything that's been done to it, starting the furthest away, which for this would be taking the square root of both sides. Because when I undo the squaring by square rooting, I get my x plus b over 2a out. Don't forget, when you take the square root, you got to put your plus or minus, because it could be positive or negative, that when we square it, we get that thing. And I'm going to actually take this big square root, and I'm going to split it into two, the bottom and the top. And I know I can do that because of my rules for square roots. Now, why am I splitting it? The top, even though this is squared, I cannot just take that because of the subtraction, but more so because of the bottom. I know the square root of 4 and a squared together is what?
2a.
Excellent. Unfortunately, I got to leave the stuff on top then. And remember our whole goal here. I know it's easy to forget. What were we trying to do?
Solve for x.
Solve for x, get it by itself, and now there's only one thing that's left to do, and that is to subtract my b over 2a to this. And remember, can we add or subtract fractions? Only when what?
Common denominator.
That's right. And do I have my common denominator? Yes. It is a 2a. What's left on top? Negative b plus or minus that square root of b squared minus 4ac. Now you know why it's that monstrosity. Not because math teachers are like, oh, we're really going to screw these students up. It's because somebody said, hey, if I have this and I have to find when it's equal to 0, and I don't know how to factor this, I need another way. And completing the square is not always the best. So they used those things in order to come up with how to solve for x whenever you have a, b, or c. Now I'm going to go back a step, and I'm going to show you guys right here. This piece, can you guys see how if we had it like this, I could then take this mess and move it back over, and I would have my y equals, instead of 0, x plus b over 2a squared, and then whatever that number came out to be. And do you guys see why this right here was what we called h a while back? You remember what we said? Since it was an x, we would take the what of this? The opposite. And that's why your h is actually negative b over 2a. All right, trying to tie it all together for you. All right, so pretty cool. I know a lot of you haven't seen that before. I wanted to give you a little bit extra because we are reviewing so much stuff in this class. All right, I wanted to show you something that hopefully you haven't seen, and that is the derivation of the quadratic formula while reviewing completing the square and factoring. Any questions about that? All right. Well, then we will move on to the very last section for today, which is 5.2. And that is what are called power and polynomial functions. So remember, we started with x to the first, which was a linear equation. And then we went to x to the second, which was a quadratic, that parabola shape. Well, now we're going to talk about what happens when we have an even higher power. So when we have, and we're not even adding all the other stuff yet, we will eventually. But let's just talk about when we were only having x to some power, right? What happens when we have x to a power? Obviously, our graphs change. We saw what happened from x to the first, which was a line, and then x to the second, which was a parabola, right? So here, I want you guys to tell me which of these functions are what are called power functions. So I'll give you about 30 seconds to go through and tell me what you think. Just power function, yes or no. All right, go ahead and take 30 seconds. All right, so let's see what you guys think. I saw some good comments in the chat. I'm glad that you guys are following along, trying to figure this out. Almost done. Let's see here. is the first one, the constant function. Would we consider that a power function according to its definition? What is a power function? X to some power. Notice here, I don't even see an X. But could I write it as an X? Could I write that as X to a power?
X to 0.
Very good, Zenon. Anything to the 0 power other than 0 is equal to 1. Very good. So yes, this is what is called a power function. Now the next few are pretty obvious, aren't they? It's x to the first, it's x squared, it's x cubed. So definitely those you can see, even without having that k coefficient in front of it, it's x to a power. So absolutely, those should have been pretty obvious and easy. But what about the remaining ones? Now there is an x, unlike the first one that we rewrote. So can we write this, or that as x to a power? This is going to test your previous algebra skills, right? Do you remember what 1 over x is if we wanted to move that x back up top to the opposite side of that division bar? What do we say we'd have to put?
X to the power of -1.
Excellent. Very good. That is indeed equivalent. Which means, were we able to write it as x to a power? Well, then what if it's squared down there? What is it going to become?
-2.
Very good. It's already a fraction, so what we want to do is change it to just be x to a power. And so therefore, yes, this is as well. Now, how about square roots? How many things do we need to get out of that square root? Two. We need something squared. Right now, how many do we have? Just one. So how many do we have? Out of how many do we need? We have 1/2 of what we need. So hopefully you remember anytime you had a root, we called it, and anything inside, whether it was raised to the power inside or raised to the power outside, you should know that we could rewrite that thing as whatever the power is over the root. We call those fractional or rational exponents. Okay? So that means yes and yes, because if it is x to the first and we're taking the cube root, we have 1/3 of what we need. So actually, every single one of these is indeed a power function. They just don't all look like it. These obviously did. Okay, so just a little bit of review mixed in there, but power functions can come in all different shapes, and obviously they are all their own types of functions already. And by knowing that they're functions, we know they pass the vertical line test. So let's expand on that a little bit more and talk about whether they're even powers versus odd powers. And remember, I mentioned about the score being the same last week. What if the score is the same? What can we say our score is? Our score is even, right? But if the score is not the same, then you're going to think of it for this scenario as odd, right? So an even score means that they're facing the same direction on the ends. Okay, we're going to call this end behaviors. How do our graphs behave at the very extremes, the far left or the far right? Well, we can tell just by looking at the powers. And we'll expand this into polynomial in just a second. So if it's even, notice they're facing the same direction. Now up, depending on if that k, that coefficient in front of our definition here, is positive. If it's positive, they're facing up. Now, that means if they're the same, then they're both facing up, right? But if it's odd, then what is that going to mean? As we go from left to right, as our x's increase, so will our y values. Still facing up, increasing, positive. Okay, but notice odd, they're facing what on the ends? Opposite directions. Now, of course, you guys know what else could k be? That constant in front of our power function could be negative. And then what is that going to do to this? Flip it, just like we talked about and reviewed last week. Now this one, it would flip this side and flip this side. So now this side would be up here and this side would be down here. Do you see how this flipped up there and that flipped down there? Which we call a what kind of function?
Reciprocal,
Careful,
inverse,
getting warmer. A decreasing function. But again, notice from as our x's get bigger, our y's were getting larger, but that's because it was positive. But if it's negative, then it's facing down if it's even, or from left to right, as we read this, down. And you guys remember what I put up there in behavior? Do you guys want to graph these things in order to tell me all of this information? Domain and range, or how it behaves on the ends? No, I don't want you to have to. Okay, I don't even want you to plug it into some graphing calculator or technology. I'd rather you just be able to look at it and tell me. And the way that they're going to want you to explain that is as x goes to negative infinity, that arrow means approaches. What, and they're going to leave this blank, what does our y value do? So as x approaches negative infinity, which means to us, how would you say that in words? English.
Left.
Very good, Bear. The far left, as our x's go that way, what do our y's do?
They go down.
They go up for this one, or very good, down for this one. Okay, so when they ask for end behavior, this is what they're going to want you to be able to tell them. All right, so as x goes to the furthest right, whether the number in front of our power, even, same, odd, opposite directions, if that number in front is negative, we know from left to right, it's going to decrease. So as x goes to negative infinity, our y's would start up at positive infinity. And as x went to the furthest right, our y values would approach negative infinity. And you can tell all of that just by whether the number in front and the highest power is even or odd. Pretty cool. All right. All the other stuff that goes on in the middle, we don't really care about just yet. We're just talking about the extreme left and right and how it ends. Okay? So speaking about all this stuff in the middle, that takes us to the last thing for today, and that's polynomial functions. And polynomial meaning many terms or many names. Okay, that's what poly means. So now we don't just have that first thing to a power. We have a bunch of other possibilities, whether they're constants or x's or all the way on down, right? And you guys are familiar with polynomials. You've seen them a lot, but I want to make sure that you know what this is called, what the highest power we call the degree of a polynomial is, right? And why are they just focusing on this first thing? Because all the rest of this is and can change, but this right here tells us a whole lot. Not only the number in front, but whether it's an even or odd power. All right. So we want to talk about the intercepts. And when we have higher powered things like a, what would this be? What degree equation? Anybody recognize it? Good. Somebody put in the chat to the third. Now, obviously, it can have all the others, the x squareds, the x, and even a constant. But we know it's an x to the third because it's that elongated s we talked about. And notice there are some very critical points on this graph. And notice I knew that this was a positive here in front of the x cubed because from left to right, it was going up. X cubed, opposite for my ends. But this and this, what are they called?
Local minimum.
Very good. Local max and a local min. And why are those so important? What did we say it does at those values?
Turns.
It turns. And what about it? It changes from what to what?
Increasing to decreasing.
Excellent. Very good. Increasing, decreasing, back to increasing. Very, very important things. Awesome. All right. So just wanted to run through that real quick. These turning points, there are a minimum number of these that can happen and a maximum number of these that can happen. Okay. We're more concerned with the maximum number. Okay. So the intercepts we know how to find, we let the other letter equal 0. To find the x-intercepts, y0, the y-intercepts, x0. But these turning points, you guys will learn more about these in calculus. Okay, you'll find better ways to find these in calculus. But the better you understand it now, the easier it's going to be when you get there. All right. So if you wanted to find polynomials intercepts, nothing's changed. Let x equal 0 or let y equal 0. But to find the turning points now, if you have a degree of n, that meaning your highest exponent for x, then you will have at most that many x-intercepts, could be less, but no more. And more importantly, I'm gonna highlight this in a different color for you. In -1 turning points. So remember when I wrote down some x cubed function. Notice there was 1, 2 turning points. How about when it was x squared? How many turning points? 1 at the vertex in particular. And how about a line? How many turning points?
Zero.
Notice it's always the n-1 turning points. Okay, very important concept for us because that then allows us to know exactly the maximum number of max and mins. Now we also know a cubic function can just look like this, the most basic one, and it only has 1 turning point. But that's why it says at most of these and these. Okay. Now, one more thing I want to make sure I mention are these things called multiplicities. Have you guys heard of those before? If I was to give you this graph, does everybody know what that looks like? How about now? Do you see my HK? Do you see my original function? Then you all know that it should be the x cubed cubic function that we talked about, just shifted what and what?
Right 1, down 4.
Okay, now what is shifted right 1 and down 4?
Vertex.
Very good. I'm going to use that term loosely, but good. Vertex. I'm going to go back to this. And if I was to graph this, I know that, just to make it simple, I would just have my x cubed function shifted right 1. And from there, I would take this and I would just graph my original cubic function. Done. But if I took this and I made it a little bit more challenging, and I gave it to you like this, now who can tell me what that looks like? What kind of function is it?
Cubit.
Very good. A lot of people in the chat are saying it's also cubed. You're just trying to fool us, Alan. It is still an x squared times an x to the first, which means we will still have a cubit. It's just not in our preferred form. But if we wanted to, we could actually multiply this all out and you'd see it's an x cubed something, 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 something. I don't care about that. I still want to be able to graph this. And who can tell me what the end behaviors would be for this?
Odd.
It'd still be odd. Very good, Julian. But what does that mean? What would it be to the far left? As x approached negative infinity, what would our y approach? And as x approached to the far right, positive infinity, what would our y approach?
Top would be negative infinity, and then the bottom one would be positive infinity.
Very good. It would still be the same as this because notice there is still a positive in front, just like that one is. But what does change are these things called multiplicities. And we're going to use the even odd thing that we just talked about to mention these. Multiplicity means multiplied. Now, when I set this thing equal to 0, that's letting my y equal 0. What am I finding? What do we call those?
Intercept.
Which one?
X.
Very good. It would be finding our x because we let y equal 0. So I already know exactly where this would all equal 0. At what values? One and -2. Which means I should be able to graph that one as well. At 1 and at -2. And we said we knew that it behaved down here and then up here, didn't we? But what does it do here? Does it hit this and go through and then hit that and go back through this way?
No.
It can't. We don't have that value. So notice, even though I know it ends here and there to the left and to the right, I know that it has to go through this one. And then what is it going to do? Is it going to go through this one? Or is it going to hit it and go back up? Is that still my cubic form? Yes. And without actually having to find what these y values are, positive versus negative, and testing things into this to see what my y's are, which you could do. You could say -2 and 1, and then find for this x value and this x value out here, are my y's above or below, or what are they? You can actually use these things called multiplicities. And you can see right here that there is actually a multiplicity of 2 at 1 and of 1 at -2 and a 3 at 1 here. And what do we say would happen at odd powers? What one word do we associate with odd?
Opposite.
Opposite. And with even powers, we said what? Same. Well, guess what, guys? You can use that for these multiplicities, these x-intercepts as well, because I know at -2, it's to the first power, which means because I know the end behavior, it's a cubic and it's a positive, that it's going to have to end, and I'll do this in red so that you can see the same color, down here. And it's got to end up here because I know the end behaviors. Because I know the power or degree that is the highest and the coefficient in front of it. But I also know at -2, it's an odd multiplicity. And odd meant that it's going to go to the opposite side of 0. These are all negatives. These are positive values. Then at this value, which is the +1, it has a multiplicity of what? Even. And if it's even, we know it's the same. So when it hits this 0 value, since it was up here, it's going to hit that and go up the same direction. Odd, opposite, goes through. You guys see how you can use all of that information to get a quick sketch of what that graph looks like? So I know that's a lot, but I'm trying to show you the even odd multiplicity stuff goes along with the even odd for the degree, the entire polynomial. For odd, opposites, even, same. Okay, so you can use that both for the end behaviors as well as the x and y intercepts for the multiplicities. All right, that's all I got for you for this one. Hopefully you got a lot out of that. We're going to go ahead and start working on our group quiz now.